Hi guys, so I'm here, but I'm very small. It's okay. Um, so as I said in class, I'm going to cover in a nutshell the unit about fluid. I didn't do that last semester, and it's very important if you are going to work in the hospital, or if you are a biology or marine biology major. Of course, everything is fluid, right? And or if you are in chemistry as well. So fluid, you have 3 units, right? We're going to cover only 2. So you have fluid static. So that means the fluid, and fluid can be water and it can be gas. So if the gas, it's a perfect gas, let's say, it will behave like water. Okay? It has same behavior. So whatever we're going to learn for water is going to work for gases as well. So fluid static is when the fluid is not moving. So you have very cool application like buoyancy. So here in that case, they are trying to find the proportion of fat in the body, because fat has a smaller density than tissue or muscle. So you will expect to weight less if you have more fat. So you can do the computation. So we're going to look at that. And then you have fluid dynamics, which is a little bit more challenging. And it has to do with water or blood, for example, flowing at a steady flow, And then you also have turbulence. So that's when water starts to spin around and you have some chaos. So that we are not going to cover. It's not covered in your book anyway. So we're going to look at fluid statics and fluid dynamics. So let's go straight to the definition. Density is the mass per unit volume. So it means if you take a cube, so 1 meter is about one length, like 1 arm length, right? So if you have a giant cube, 1 meter per 1 meter per 1 meter, you find the mass, and that's going to be the definition of density. So here are some examples. Air. So we live in the ocean of air, like the atmosphere is like an ocean, and the density of air is about 1, right? So 1.2 or 1.3. So let's say 1.3 kilogram per cubic meter. So if you take, if you have a very small cabinet or closet, and it's 1 meter wide and 1 meter long and 1 meter in height, and it's only filled with air, so the mass of that air is going to be 1 kilogram. Okay, so it's going to be about 2 pounds. So it's not much, but still, the air does weigh something. So if you have like a very big balloon, like maybe the envelope is very light and it's filled with air, it does weight. It does have a weight, right? So if it's 1 meter cube and you put that on a scale, maybe you're going to have 2 pounds plus whatever the envelope has weight as well, right? Now, the most interesting thing, of course, if you are doing chemistry lab, for example, or if you are working in the biology lab, that's going to be water. So water is here, not solid liquid, blood here, and water has more density. Not about the same density as blood. Blood you have about 1060, and water has a density of about 1000. So blood has a density a little bit larger than water. You see, a little bit higher. So the density of water, it's going to be 1000 kilogram per cubic meter. So again, 1 meter is about 1 yard or the length of your arm about, and you take a cube, and of course you all know if you try to move, if you have fishes, for example, you try to move the aquarium, you know how heavy it is, right? It's very hard, so especially if you have a very big aquarium, right? It's very hard to carry. So when it's empty, of course, it's not that heavy, but if it's full of water, it's going to be very heavy. You cannot do it, right? If it's 1 meter per 1 meter per 1 meter, you cannot lift it. And the mass here is going to be 10 to the third kilogram, okay, for 1 cubic meter, which is about 1 ton. Okay, so imagine 1 ton, okay? Forget it, okay? You cannot lift that. One thing that is maybe you have to keep in mind is that 1 meter is about 100 centimeter, right? So am I recording? Yes. So 1 meter square is 1 meter times 1 meter. So that will be just an area 1 meter per 1 meter. That's going to be 100 centimeter times 100 centimeter, which is 1, 2, 3, 4. So 10 to the fourth square centimeter. Right, and then if you add one more, so 1 cubic meter equals 1 meter times 1 meter 1 times 1 meter, that's going to be of course 100 centimeter times 100 centimeter times 100 centimeter, which is 10 to the 6 cubic centimeter, which is 1 million. Okay, so you have to be careful when you are converting cubic meters to cubic centimeters. So we are in water, so which is very convenient. So when you do the conversion, so here we have 10 to the third kilogram per cubic meters, and you can do the math and try to convert in gram per cubic centimeter. And you know that 1 cubic meter is 10 to the 6 cubic centimeters, and you know that 1 gram is 10 to the negative 3 kilogram. So do it as a practice problem. Okay, it's a dimension problem, so you can go step by step. But if you do that, you're going to find that the density of water is also 1 gram per cubic centimeter. And if I do it on scale, 1 centimeter is about this, right? That's 1 centimeter. This is not 1 meter. 1 meter is 100 centimeters, but this is 1 centimeter. So if I take that much of water, so 1 centimeter per 1 centimeter, it's about that, you know, that's going to be 1 gram. And interestingly, 1 cubic centimeter is also 1 milliliter, right? So that means that the density of water is 1 gram per cubic centimeter. Is also 1 gram per milliliter. So 1 milliliter is 1 gram. So when you are doing experiment in the lab, for example, and here it says 250 milliliter, and you fill your beaker with water, right? So up to here. So you're gonna, because you know the density of water, and so if you fill your beaker up to here, the mass of the water inside, it's gonna be exactly 250 grams, right? Which is 0.25 kilograms. So you don't have to use the technique, you know, find the mass of the beaker when it's empty and find the mass of the beaker when it's full. Subtract. You don't have to do that with water, right? Right away, you know, if it's 250 milliliter, that's going to be 250 grams. Okay, so it's nice to know. Okay, so try to do this one. You can pause the video and do it. Don't wait for me, just do it. So the weight is 690 newtons. So I suppose you have paused the video. And that's how much blood he has in his body. So that will be the volume, right? That's the volume. And that's his weight. Find the blood weight. So the weight, by definition, of blood. So any weight, it's going to be the mass, except here it's going to be the mass of blood times gravity, which is 9.8, okay? And then you have the density of blood. So the density of blood is mass of blood divided by the volume, right, of blood. So you can do it step by step. Let's check the density of blood. We said it's 1060, right? So what you can do, you can do it step by step. Okay, you can, if you use that, you have 1060 equals mass divided by the volume of blood, which is given. So it's going to be 5.2 times 10 to the negative 3. So you cross multiply divide. So the mass of blood is 1060 times 5.2 times 10 to negative 3. I should look at the time 611. Okay, so the weight of blood is going to be the mass, and the mass is 1060 times 5.2 times 10 to the negative 3 times gravity. And if you do that, you're going to find 54 Newton. So the weight of blood divided by the weight of the guy is going to be 54 Newton. I want to make sure the units are the same, over 690. And if you do that, you know, cross out, it's a proportion, there is no unit. It's going to be 0.08, which is 8%. So 8% of our body is blood, and the rest is water. Okay, so that's good. Typical questions here. Okay, so let's look at the definition of pressure. So you imagine that you have a pile of books. Okay, so you have your table here and you have books, right? So you have one book. Okay, it's not going to put too much pressure here, right? Maybe you have some Play-Doh here and see what's going to happen. It's going to be squished, but not that much. Of course, if you increase the number of books on top of that Play-Doh, you know you are increasing the pressure. Does it make sense? Now, let's compare, like, let's say you have your hand. So that just to give you an idea what's going to be pressure. So the weight is going to increase, right? So for example, one book compared to 1, 2, 3, 4. So of course, the weight is going to be multiplied by 4. And if the surface area is the same, pressure is also multiplied by 4. Okay, you don't need to take any physics class. It just makes sense. Then if I ask you, you know, you have a very big book, like during my time, a long time ago, we have things called dictionary, and they were huge and heavy, and it was very convenient, you know, if you want to have a paper iron, you will put that under your dictionary. It was a very big book and very heavy book. Okay, you hold that in your hand and you feel the weight. What do you think is going to happen if I take the same dictionary, right, and I do this? I put the dictionary on the corner. Do you think it's going to hurt more, or you're going to feel the same? So that's your very big dictionary. So the weight is the same, but now it's just one corner, right? of course it's going to hurt more even though the weight is the same. See, the weight is the same. It's the same dictionary, the same weight. But of course here the area is smaller than the area here. So that means that all the weight here is concentrated on a very small area. So we define pressure as, in that case, it's going to be the force or the weight per unit area. Or pressure, the pressure is defined as the force, so that will be in Newton, divided by the area in meter square. So unit for pressure is going to be Newton per meter square. And you see that even though the pressure, the weight is the same, the pressure is not the same. So I think the best example for that is when you compare high heel to sneakers, and here I have found that I guess it's like Italian, maybe it's, I don't know if stiletto looks like Italian shoes. So let's say it's an Italian website. I'm not sure, but they compare fine. Okay, try to do that. Pause the video. What's the pressure acted upon the floor if you have a woman weighing 60 kilogram standing on the floor compared by the pressure exerted by 1 foot of an elephant? And the elephant is 3 tons, right? So 3,000 kilograms. And here the woman is 60 kilograms, so it's pretty skinny. It's like 120 pounds, so it's skinny woman. And you see it by 1 leg. Okay, so the weight, of course, is not the same. An elephant is 3 tons, okay? It's huge. And the woman is 60 kilograms. You cannot carry an elephant. You can carry a woman if you can, okay? But when you're going to find the pressure, do that. So you do 60, okay? So they didn't multiply by 9.8, but because you have 9.8 here, 9.8 here, it doesn't really matter, right? So first of all, a woman, we suppose, has 2 legs, right? So 60 divided by 2. So the weight by 1 leg, the weight that push on the floor will be 60 divided by 2, right? And then you divide by the surface area. So the surface area of the shoes, like especially here, in contact with the floor. And you have that much pressure. Now you do the same thing with an elephant. So you have 3,000 divided by 4, because we suppose the elephant has 4 legs. And then you divide by the surface area and you have that much pressure. So interestingly, you're going to have more pressure, and I think they took the tip here. They didn't even take that part here. So that tip here can really hurt you if it goes into your skin, okay? So that's why I put that song here. I love that song here. So pressure depends on the area, okay? So it's how much force per unit area. And here, even though the weight is huge, the weight is spread out over a big area. And here, even though the weight is smaller, it's really concentrated in a small area. Okay, so I hope it makes sense to understand the meaning of pressure. So here is a definition. Pressure is force divided by area. So usually the unit are Newton per meter square. And Newton per meter square is a unit called the Pascal. So named after Blaise Pascal, who was French, and he was a French philosopher, but at the time philosophy was also science, so he did also a lot of work in science. So Pascal, he did a lot of work in geometry. I'm not sure. So anyway, Blaise Pascal, so that will be the unit here. Or you can use the British unit, which is pound per square feet. So just to give you an example here, the atmosphere, I told you, like we live in the ocean of atmosphere here, so you have all this air pushing on us, push on us, pushing everywhere. And if you take a little square here on Earth, or on us, could be on us as well, and that little square is 1 inch per 1 inch, the weight of the atmosphere here, all that weight here, it's going to be 15 pounds. So the atmospheric pressure is 15 pounds per square inches, right? Just to give you an idea. It's also, so we are also, we feel that pressure, right? But the pressure is everywhere in all directions. So we don't suffer, because inside our lungs, you know, it's not going to crush us, because inside our lungs you have exactly the same pressure pushing against. So because there is a net force of 0 on the human body, so you don't feel the pressure. We're going to discuss in cases like diving or going into space, where it can be very deadly if you have an unbalance between inside pressure and outside pressure, right? By the way, you know, when you have a clogged bathroom, you have those things here, you know, to unclog the bathroom like this. So what's going to happen? It's going to stick. It can stick to your to the wall of the bathroom, for example. Why is that? Because the pressure from the atmosphere is pushing the plunger. It's called a plunger, right? And because you push with your hand here, so first you push with your hand, so all the air here is out, so there is no counterbalance. And because the pressure is as much as 15 pounds per square meters, it's going to be a huge. And then it's very hard to unstick, right? So that's how pressure is defined. And of course, you can also find the pressure of a gas. So if you have a container of gas, like here we have a tire, you have more pressure here compared to the outside world, right? So here we have what is called 1 atmosphere, so 15 pounds per square inches. But here, because you are trapping the molecules of air inside the tire, you're forcing the air molecule inside when you are putting air in your tire. So all those little molecules are going to bump in all directions, and each time they bump, they're going to exert a force, right? And we can define the pressure as the force per unit area, which means that here you can cut out, for example, 1 inch per 1 inch. So outside you're gonna have 15 pounds, but inside you're gonna have a higher pressure. So because it's those little molecules, they bump, okay, they collide with the tires, so bump. So you're gonna have maybe 20 pounds per square inches, right? Just an example. I'm not sure how much you're going to have, but you can find the pressure of your tire. So when you are using a gauge, okay, you're going to find how much more pressure you have inside your tire relative to the pressure of the air outside, right? It's called a gauge. So, see, PSI, it's for pounds per square inches. So that here is going to compute how much more pressure inside you have compared to the outside. Okay, so I have like a small simulation. Let's see, gas property. You can find those if you Google Sims. Sims physics PHET, you're going to find those. Okay, so I'm adding some air molecule inside, and you see what's going to happen. They're going to move in all directions, and they do it randomly. and they're gonna bump here on the wall. So that's why the pressure is increasing. I can do two things. I can increase the number of molecules inside. So I increase the number of collision on the wall of the container, and by doing so I am increasing the pressure, right? Or I can also, and it's a proportion, so more molecules, more pressure, so the pressure for the same volume will be proportional to the number of molecules. It has to do with the ideal gas properties, you know, PV equals nRT. And if you decrease the volume, I cannot decrease the volume. Okay, so now I can decrease the volume. So if I decrease the volume, you see how the pressure increases by a lot, okay? Because those little air molecules, they're gonna be squeezed together, so they're gonna collide more, okay? So they're gonna exert a higher pressure, and that's gonna be the pressure in atmosphere. Okay, so 1 atmosphere, that will be the atmosphere of the air outside, and here I am more than twice as much inside. Okay, so this is called a gauge. So that's how you measure the pressure of a tire. Okay, so if there is no gas in your tire, it's going to be 1 atmosphere. 1 atmosphere is 15 pounds per square inches, is the pressure from the atmosphere. And of course, if you increase the pressure inside, you're going to be higher than 1 atmosphere. Okay, so 1 atmosphere is the pressure due to the atmospheric weight, okay, pushing on the ground, and that will be 15 pounds per square inches. Okay, so Pascal means Newton per meter square. You have the kilopascal, which is 1,000 Pascal. Example, the atmospheric pressure is, so that means the pressure from the atmosphere. So imagine again, the atmosphere is very thin. So it's like you have an orange. Let's say you have an orange, the atmosphere will be just the skin of the orange. So it's a very small atmosphere. And as you go towards space, the density decreases, okay? Nevertheless, if you are standing on Earth, right? So this is you on Earth. And if you take a small area here, 1 inch per 1 inch, again, I'm just repeating, and that will be, and you put a scale. So let's say you have a very small scale here, that size here. You can go up to space, okay? So this is space, and this is all the air we have in the atmosphere. So the weight here will be 15 pounds per square inches. That's going to be the same as, it says here, 10 to the 5. So it's going to be 10 to the 5 Newton per meter square. So it's a huge number. So it means if instead of taking 1 inch per 1 inch, I take a big square here on Earth, 1 meter per 1 meter, and I go up to space, so it's a big column of air that I cut out from the atmosphere up to space here, and I have a scale, so I have a giant scale. The weight here will be 10 to the 5 Newton meter square. Okay, and that's the same thing as 10 to the 5 Pascal. So Pascal is the unit, and it's the same as Newton per meter square. So 1 Pascal is 1 Newton meter square, because we have all those scientists that we want to honor. So okay, Pascal has his own unit. Okay, so we can also use atmosphere to measure the pressure of a gas, and the atmospheric pressure is 1 atmosphere. Okay, so again, what's a 1 atmosphere? So one atmosphere, that will be 10 to the 5 Newton meter square, which is the same thing as 15 pounds per square meters, right? So we use atmosphere so we can compare the pressure relative to the air outside. Okay, so for example, if you are measuring the pressure in your tire, let's say if it's 0.5, that means you are 0.5 atmosphere above the regular at 1 atmosphere. Okay, so that will be 1.5 atmosphere. But your gauge is going to read 0.5 because it's 0.5 above 1 atmosphere. Okay, so usually the pressure here, when it says 10 to the 5 Newton per meter square, that will be the same as 1 atmosphere. Okay, I hope it's clear. It says here. Okay, so 1 atmosphere is about 10 to the 5 Newton per meter square. We're going to see next what it means here, which is the same thing as 15 pounds per square meters, which is about 15 psi. And psi is the same thing as pound per square inches. So now you can understand how it works, right? So that will be how much pound per square inches you have inside your tire above the 1 atmosphere. Okay, so question, you can answer that question. If you have 1 foot, is your weight going to be the same? The answer is yes, you have the same weight, right? But is the pressure the same? The answer is no. If you are standing on 1 leg, you're going to have double the pressure. Okay, so let's do an easy problem here. You want to find the... did I skip something? I skipped something. Okay, I think I skipped from your book. Let's say 13.1. I don't know where it was. Maybe it comes after. I think it comes after. Okay, so let's try to do this. And again, you should pause the video and try to solve this problem here just by using the definition. I hope the video is working, because I don't want to start over. So here you have the hand of a swimmer, and the area is given, so it's going to be 8.4 times 10 to the negative 3 meters square. And you have the pressure, and the pressure is, so you are given a pressure 1.2 times 10 to the 5 Pascal, which is, so she must be quite deep here, because at that height she has a pressure of 1.2 times 10 to the 5 Pascal, which is 1 atmosphere, right? So remember, 1 atmosphere, let's go back to here, 1 atmosphere is 10 to the 5. Oh no, because they sorry, let's go back. She's not very deep in the water because you already have 1 atmosphere here, right? So 1 atmosphere is 10 to the 5, let's say 10 to the 5 Newton per meter square, right? So that's the pressure from the atmosphere. And because she's not very deep, so she's just swimming under the surface of the water, the atmosphere is the same here, right? So the pressure on her hand is 10 to the 5 Pascal, so 10 to the 5 Newton per meter square. and you have the area of the hand, which is 8.4 times 10 to the negative 3 meters squared. Find the force. Okay, so you can pause the video and it's easy. So you just use the equation that the pressure is the force divided by the area. So we have the pressure, which is 10 to the 5. That's going to be the force, and that's going to be the area, which is 8.4 times 10 to the negative 3. Right? So the force is going to be 8.4. You have a 10 to the 5, and you have a 10 to the 3. So the force is going to be 8.4 about 10 to the second Newton. So the pressure always is the force. So the force is a vector, right? So I should have said that when you are using this equation, the pressure is a scalar, right? But force is a vector. So remember from physics 1, a vector has a magnitude and a direction. So when you are using that equation, you are taking the magnitude of the force, right? But it does have a direction. And the direction is always perpendicular to the surface, right? So she has her hand here. That's going to be the force from above, because they're just asking the force on the back of the hand. Of course, you're going to have a force on the other side of the hand that will be a little bit larger, and I will explain why. That's why you can float, right? But that's another story. And you also have pressure from to the tip of the fingers, I guess. But the force here is always perpendicular to the surface area. Okay, so then you have the solution here. Yeah, they just round. Okay, and then 13.1, so that's from your book. So 13.1. So it's the book that is, it's called, it's the book from the syllabus. Okay, it says with a simple calculation. So why don't you try to do it, right? So you can pause the video. So can be tricky, okay? So try to do it. Weight of air. So the density of air we've seen is 1 kilogram, right? It's about 1 kilogram per cubic meters. It's a little bit more, but I'm going to say, okay, it's 1.2 actually. And the density of water is 10 to the third kilogram per cubic meter. So it's 1 ton. So a living room, so you have a living room, and it's 4 meter by 5 meter, boom boom, and the ceiling is at 3 meter. So that's your room here. Okay, and they want to know, what do they want to know? The mass of air. Okay, so that's easy. So that will be the mass of air. So mass, so we have density equals mass divided by the volume. So from here you have mass equals density times volume. So for air, so the mass of air, it's going to be the density of air, which is 1.2 times the volume. So it's going to be 4 times 3 times 5, which is 60. So you get about 72 kilograms. So if you have this home, it's a hurricane in Florida, and everything is flooded. So the mass of this water here, it's going to be, the density now is 10 to the third times 60. Okay, so that's going to be 60,000 kilograms. Okay, so the book you have is not bad, so you can use it. You can do on your own 13.2. So I'm going to show you 13.2, but so you can just take a screenshot, but it's in your book and you all have your textbook. Okay, so you can do okay, let's do it. Let's do it. You can pause the video and try to do it. 6:40, I have to check the time. Okay, so the force that the atmospheric pressure produces on the surface. Okay, consider the room described. What is the total force on the floor? Blah, blah, blah. Okay, so you still have this this room, so 3 meter, 4 meter, and it has a ceiling, of course. So no, this is 5 meters, and it says inside the room you have 1 atmosphere, which is always the case. It's about 1 atmosphere because your room is connected to the outside, so everywhere you go it's always 1 atmosphere, and 1 atmosphere is about 10 to the 5 Newton per meter square, right? So that means for every meter square that you take here, so if you have 1 meter per 1 meter, you're going to have a weight here pushing on it of 10 to the 5 Newton per meter square, right? So you can say like this, 10 to the 5 Newton for a square of 1 meter times 1 meter. What's going to be the force if you have an area of 5 meter times 4 meter? Okay, so the force is going to be 10 to the 5 times 20 Newton. So it's going to be 2 times 10 to the 6 Newton. Or you could have said pressure is force divided by area. The pressure is 10 to the 5, the force IDK, and the area is 60. Okay? So I'm trying to follow your book. Okay, Pascal Principle. It's very important because it has many applications. It doesn't say he was French, but he was French, 17th century here. So it says here that if you have a fluid here, if the fluid is not moving, if you push that piston here, the same pressure will be transmitted in all points of the fluid. Okay, so you have to read that. Any point, so the fluid has to be at rest, okay, it's not moving. So if you are pushing that piston here, of course you are expecting that pressure, that piston to go up. It's not the force that is transmitted, it's the pressure, okay? So it means if you have a pressure here, it's going to be the same pressure here, that's going to be the same pressure here, that's going to be the same pressure here, and that's going to be the same pressure here, and of course that's going to go up. Okay, it makes sense. And this is called Pascal's principle. What? Ok. Non, mais je recorde pas l'image. Ah, d'accord. Okay, so why is it so important? Okay, I have a... Okay, so this comes from the book Paul Hewitt, right? And he wrote a very nice book called Conceptual Physics. I highly recommend it. So let's say you have a piston here and the fluid is not moving. And you see that the same pressure is going to be transmitted all over, right? So that pressure here is going to be transmitted here, but also transmitted here, and transmitted here, and transmitted here, and transmitted here. So it's the same pressure all over. But the area here is 50 times smaller than this area there. So what do you think is going to happen here? How much you can lift here? You see that what you are doing here, it's like a lever. Okay, you are multiplying the force. Okay, so let's do the math. So you have the pressure here pushing, so that will be the pressure, even though that will be a force, right? But the pressure is transmitted here, but it's also transmitted here, and you see it's transmitted here, and you see it's going to be transmitted here, and here it's going to be transmitted there. Okay, and all over, and it's of course it's going to be in 2 dimensions. So here the area is multiplied by 50. What do you think the force is going to be here compared to there? So remember, the force, the pressure by definition is the force divided by the area, and the pressure is the same. Okay, so here you're going to apply a force. I'm going to call that F1, and here I'm going to apply another force. You're going to have a force F2. So from here, so I'm going to call that P, and the same pressure here is P. So here I have P equals F1 A1, and you're going to have the same pressure here pushing up, same pressure that you have here pushing down, because Pascal says that the pressure has to be transmitted. It's going to be the same pressure. So then here underneath you're going to have F2 over A2, right? It's the same pressure. So you're going to have F1 over A1 equals F2 over A2, and we are talking about area. So you see that F2 over F1 is going to be equals to A2 over A1. So that's going to be Pascal principle. So it means that because the pressure is the same, if you multiply the area by 50, so then the force is going to be multiplied by 50. So if you go to a mechanics, for example, you see how they lift the car, and it doesn't seem very hard to lift the car. It's a hydraulic press. So the way it works, it have a big platform, and if the platform here is multiplied by 50 compared to the area here, so this is area of 1, that's an area of 50 meters square, for example, so 1 meter square. The area is multiplied by 50, so the weight that you are going to be able to lift is also multiplied by 50. So for example, if you have 10 kilograms here, you're going to be able to lift 500 kilograms. So that's the principle of many machines. They are using hydraulic press, and that's because of Pascal's principle. So little force here will mean a very high force there. And we have seen that in physics 1 with lever, but there is a price to pay, because nothing comes for free, of course. Because of conservation of energy, the work that you are doing here, it's going to be equals to the work that you are doing there. So work is force times distance, right? So the work you are doing on the piston here is going to be the force you are applying times the distance you are pushing down. And on the other side, the work done on the car, because of conservation of energy, is going to be the same, but it's going to be F2 times D2. So F2 is multiplied by 50, so this has to be divided by 50, so energy is conserved. So a big distance down will mean a small distance up. So that's why when you are lifting a car, for example, the same principle, you have to keep pushing, right? And the car doesn't move that much. But that's making, it's like a machine because it makes you stronger, even though there's a price to pay. So that's the idea, right? So the pressure is transmitted all the way in the fluid. Okay, so for example, let's do a quick example here. Why don't you try to do it? Let's try to do it. You pause the video and you're doing it. So what do we have? We have that, so have a small push here, which means a big push there, but the pressure here, it's going to be the same as the pressure there. So pressure here, and pressure here, and pressure there. It's going to be the same pressure. So you have F1 over the weight of the car. So I always call F1 and here I'm going to call F2. Okay, so I'm going to start with F2. Now I'm going to say F1 over F2 equals A1 over A2. So small over big equals small over big. Or you can do the opposite. You can do big over small equals big over small. Okay, you will get the same thing. So input force is F1. So F1 is the unknown. So I'm going to put F1 divided by the car. So it's going to be 1050 newtons. So that's going to be the effort. F2 is called the load, right? So A1 is, so the radius, so you have to find the area. So it's going to be pi times 0.012 square. That will be A1 over A2, which is of course bigger, so 0.150 square. Okay, you have to find the area. So, and then you multiply this by that and you divide. Okay, you cross multiply, divide, get F1, and you should find that F1 equals 131 Newton about. Okay, so make sure you do it. Okay. Okay, next, almost done for the first part. I want to finish anything having to do with water. So it makes sense. If you have like a big reservoir of water, as you're gonna go deeper in the water, you're gonna see that the pressure is gonna increase because pressure is the weight per unit area, right? So if you have one book versus two book versus three book, 4, 5, 6, 7, of course, the weight for the same area, so the same area here, as you increase the number of books, you're going to increase the pressure, right? So likewise, if you have here, you take 1 meter per 1 meter, as you go deeper and deeper, you're gonna have, imagine you are cutting out a column. Okay, let's do that better. So if you are at a height here below water here, like let's say you have like a fish here, and if you take a small area, imagine you cut out a small area 1 meter per 1 meter, of course you're gonna have all this pressure, all this weight here, right? Pushing down. Plus, of course, you're going to have the atmospheric pressure of 1 atmosphere. So the force acting on that 1 meter per 1 meter area will be the weight of the water here plus the weight of the atmosphere, which is just one atmosphere. Okay, remember it's 10 to the 5 Newton per meter square. But here I'm just talking about the water. So the water is going to increase as you go down. So it makes sense that the pressure inside the water is going to depend on how deep you go. By the way, if you are diving, you feel it on your ears, right? Your ears is like a pressure gauge. As you go inside the water, you're going to have more pressure on your eardrum and it starts to hurt, right? Likewise, if you go up in the air, if you're taking an airplane, you're going to have less pressure. So the pressure push from inside to outside and it hurts as well. Okay, so here we are okay because, and you cannot see me, so that's a problem. Can make myself bigger. I cannot make myself bigger. I don't know how to do it. So anyway, as the height increases, the pressure is going to increase because it depends on the weight of the water, right? So what do you think the expression is for pressure? So it's going to be depending on the depth here, how far you're going to go down. It's also depending on the density of the fluid. For example, if you have the same height of blood compared to the same height of water, blood is going to exert more pressure because the density is higher. Or if you have that much of mercury is very heavy, it's a metal, so the pressure is going to be heavier, of course. And of course, it depends on which planet you are, because of course, if you are on Jupiter, for example, the weight will be larger, so it's going to push harder. So the equation of the pressure inside the water is very simple. It's going to be the height, so that will be the height below the surface, right? So that will be the pressure only due to the weight of water pushing. So this can be the height, the density, and gravity. Okay, so a few subtlety here, which is not obvious. Okay, it's not that intuitive. So if you have a piece, for example, anything inside the water, you're going to have pressure. Okay, the force, because of the pressure, is always perpendicular to the surface. So it's going to be perpendicular to the surface here. It's going to be perpendicular to the surface here. And then you can do that experiment at home if you take a container, maybe a styrofoam cup or something very deep, or just take a bottle. You can take a bottle of water and do that experiment. You fill it with water. Now first you make a hole. You make a hole here and you make a hole here and you make a hole here. You can see you're going to have more pressure here than you have here and even less pressure there. And you see that the liquid is going to move in this direction, so it's going to be always right angle, right, compared to the hole here. It's going to be always pushed out at right angle. And you see that the pressure here is larger because the height here is bigger. So if you are diving, for example, or I don't know, if someone is under the water, the pressure only depends on the height below the surface, right? So let's say this is the surface. Maybe you have a bird. Now if it's a bird, and you are underwater here. So you're going to have always pressure perpendicular to your body. So that pressure here will be the same as this pressure there. And then as you go deeper, that pressure here will be a little bit more than the pressure there, but both of them are equal. So it means this pressure on that side will be the same as this pressure on that side, because it only depends on the height, right? So imagine you have a giant underneath the water, and then the pressure here will be a little bit bigger than there because the height is below the surface is even larger, but you're going to have the same height here. So that's how pressure works underneath the water, right? So if you are diving here, so that's you diving, you're going to have pressure here, 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 everywhere, right? It's always perpendicular to your body, except that the reason you are floating is that here you have a little bit more pressure here from here than you have from there. That's called buoyancy. Okay, we're going to see that next. But that's the thing to understand. So if you put an object in the water, you're going to have pressure here, perpendicular, 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 and it's not obvious, but the pressure underneath the water only depends on the height. Anything else not. Only on the height of the density, of course, and on the planet, but we suppose it's water and we suppose we are on Earth. Then you have to add the 1 atmosphere here. That's also adding more pressure here. Okay? So it's not that intuitive. Okay, so here, for example, tower is greater if the tower is what? Is taller, right? So if you increase the height, you're gonna have more pressure. You're gonna have, if you increase the size, you're gonna have more weight, but the force per unit square will be the same. So it only depends on the height. Do you understand what I mean? So it means if you take something bigger, so let's say you have a reservoir here, so even bigger, of course, your weight will increase. You're going to have more weight, but the pressure will be the same, because the pressure is the weight divided by the area. Okay, so if the area is the same, that's going to be the same pressure, right? So the pressure only depends on the height. So it's not that intuitive. That comes from, again, the book from Paul Hewitt. Surprisingly again, the pressure inside the water only depends how deep you go below the surface. So even though this container is huge, it's a huge container, at 3 meters below the surface, you're going to have exactly the same pressure that you have here if it's 3 meters below the surface, right? So even though the volume is small, the pressure below the surface is always only depending on how deep it is. So here it's going to be exactly the same pressure than here. So it means that the pressure here, if you are at 1 meter, the pressure the water is exerting, you remember the pressure goes in all directions, it's going to be exactly the same pressure that you have here. So if you have a dam that is trying to contain the water, it does not matter if you have a small volume or if you have a big volume. That's not intuitive, right? So as you go deeper, the pressure is going to increase. So here you need something thicker. You see how thick it gets to hold the pressure. So if you go here, that's 1 meter, and here it's at 2 meters, I'm going to have the same pressure that I have here. So again, you need to increase the thickness here. Now, so 2 meter, as you go to 3 meter here, you're gonna have a huge pressure. Same way, you're gonna have a huge pressure here. So it's called a gradient. Okay, you increase the pressure, you increase the pressure, increase the pressure. So it's not obvious, but remember, if you have something underneath the water, let's say you have something there, I don't know what it's doing there, maybe it's a big rock. Remember, pressure is going to be applied everywhere and it's going to be perpendicular, right? And if you take in account the depth, that pressure here at H1 will be smaller than the pressure here at H2. And on the other side, you're going to have the same thing here, same pressure here that you have here, same pressure here that you have here. And as you increase here, that pressure here will be the same as this one, perpendicular, this one, perpendicular, because they are all at the same level below the surface area. Okay, so that's important and it's not that intuitive. So here, if you have that, comes from that book again, if you have a cave like underneath the water, it's going to be the same pressure because the pressure is transmitted through a fluid at rest. It's going to be the same pressure and the pressure only depends on the depth. So this is a demonstration which is very famous. You see, the size of your container does not matter. The water is always seeking the same level, right? Because the pressure is the same. It only depends on how deep it is, right? So here, because the bottom of those containers, they have the same depth, okay, the same size here between here and there and here and there and here and there. So here it's going to be the same pressure, and here they also have the same pressure because this is the air, atmospheric pressure, right? So it's going to be the same pressure here than it is here, same pressure here and than it is. No, I mean the same pressure here, 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 because it has the same depth. So all those containers will be at the same level. So what do you think here if you want to answer the questions? So the answer is that it doesn't matter the volume of water. It's try to contain. What matters is the depth. So even if you have a smaller volume of water, it's still going to be the same pressure pushing on the dam. So that's why you need a thicker wall here to contain the pressure. Okay, you try to find the location, the pressure at A and the pressure at B. And again, you just have learned that, it doesn't matter the locations, and doesn't matter, the shape of whatever is above. What matters is how deep you are inside the water. So here it's 5.5 meter below the surface. So the pressure at A will be equals to the pressure at B. Okay, so you can do the math. And you can pause the video. So pressure at A, okay, so it will be just because of the water. And then here you have, what do you have here? You have one atmosphere, right? Which is 10 to 5 Newton per meter square. And in addition to that, at A, you're going to have the pressure because of the water above. Okay, you can think of that water here pushing down, the weight of the pressure, the water pushing down. Even though you're going to have the same pressure here, even though you don't see the same shape, it's still going to be the same pressure. So the pressure here because of the water, that's the pressure due to air, and they need to add together because you have air pushing down and you have water pushing down. So the pressure due to the water is going to be rho GH. Okay, so it's going to be rho. The density of water is 10 to the 5 times 9.8 times the height is 5.5, right? And you have to do the computation. And so the total pressure, it's going to be the pressure because of the atmospheric pressure, so all the air pushing down from here to the space, and then you have the pressure because the water is pushing down, so you need to add this. So it's going to be equals to 10 to the 5 plus 10 to the 5 times 9.8 times 5.5. So why don't you do the computation? Okay, so I do the computation. I hope no, I did a mistake somewhere. The water is 10 to the 3. The density of water is 10 to the 3, so that's going to be 10 to the 3 here. Okay, the density of water is 10 to the 3rd kilogram per, no, 10 to the 3rd Newton, no, it was right, kilogram per cubic meters. I'm start to be tired. So, okay, so that will be the density of water. Okay, so I hope you didn't do the same mistake that I did. So that will be the density of water. So do the computation. And if you do that computation, so the pressure here, it's going to be about 1.5 times 10 to the 5 Newton per meter square. So it will be 1 atmosphere and 0.5 atmosphere. See? Or you can say that total will be, so remember that 10 to the 5 Newton per meter square is 1 atmosphere. So the total pressure, it's going to be 1.5 atmospheric pressure. So I am 0.5 more. Okay, so here we live here on Earth, and it's nice, it's 1 atmosphere, right? So 10 to the 5 Newton per meter square. I go down, it increased by 0.5. Okay, so it means about 5 meters below the surface, the pressure is 0.5 atmosphere more. Okay, so it starts to, if you go that deep at 5 meters, it starts to hurt your ears. So that will be the answer, but I want to build on that. So if you are diving, you know that for each 10 meters you go down, you're going to increase the pressure by 1 atmosphere. Okay, so it means at 10 meter, so H equals 10 meter, the total pressure, it's going to be 2 atmosphere, right? But 1 atmosphere we are used to. It's that here, that start to hurt, right? 10 meter, you add 1 atmosphere. So it's about 33 feet. You go down 33 feet and you add 1 atmosphere. So if you have 5 meters, of course, you're going to add 0.5 atmosphere. So you can try. What is that? 15 meters. Okay, it's going to be plus 1.5 atmosphere. And 20 meters is going to be plus 2 atmosphere. So the total pressure at 20 meters is going to be the 1 atmosphere from the air plus 2 atmosphere from the water. So total, if you go down, if you dive at 20 meters below the surface, the total pressure is going to be 3 atmosphere. So remember, 1 atmosphere is 15 pounds per meter square. So if you dive at 20 meters, okay, 10 meters about 33 feet, so 20 meters about 66 feet, you're gonna feel, you know, how much you're gonna feel? You're gonna feel 15 times 3 pounds per square meters. Okay, so that's gonna be a lot of pressure pushing. Okay, so I hope it's clear. I'm trying to rush, right? So I didn't have much time to prepare the lecture, but I hope it's clear. So that's going to be the answer. So it doesn't matter if you are here or there, the pressure will be the same. Okay, so it will be 0.5 more than the pressure you are used to if you go that far under the surface. And of course, the pressure here, perpendicular here, will be the same as the pressure there. Okay, it's always perpendicular. So the pressure there, here, will be about the same. And as you go down, you're going to increase the pressure. So that's how it works. Okay. So when you are on Earth, we are acted upon. Again, if you are not under the water, so if you are standing here, you have your lungs here inside, and you have a pressure from the atmosphere. Also, it's like a fluid, so we are in the ocean of air, so it's perpendicular to us, and it's going to be 15 pounds per square inches. So how come we are not collapsing? This is because in our lungs, you're going to have also 15 pounds per square inches. So, but what's going to happen as you go underneath the water, right? So if you go underneath the water, as you go down 10 meters, you're going to add 15 pounds per square inches, right? So inside your body, what's going to happen is that your lungs, so let's say you dive at that here, and you don't have a tank, so you don't have any device here, so you know it's free diving, it's a sport. Your lungs is going to decrease, right? Your lungs is going to be squeezed. And there is a world record, I forgot her name, by a woman, and because she actually has larger lungs than other people, her lungs can be squeezed to the size of an orange as she's going down. Okay, so as you go down, the pressure is increasing. Okay, so here I have a diver. So 10 meters is about 33 feet or 30 feet. You increase the pressure by 15 pounds per square meters. So that's going to be 15 pounds per square meters that you're going to feel pushing on you. Okay, so there's this guy back then, you can read about him, he's a French, he's very famous in France. His name is Jacques Cousteau, and he's the one who came up with the idea to dive deeper if your tank has air at a high pressure, right? So that means you increase the pressure of air, and that has to be mixed up with nitrogen, of course, because that's what we are used to breathe, but it will be at a higher pressure, so it will match up whatever is outside. Do you understand? So now if you breathe at a higher pressure here, so let's say you are at that depth here, so it's going to be 2 atmosphere. So now you fill your tank if you fill your tank at normal pressure, it's going to be 1 atmosphere. But here you fill your tank, you push the air molecules inside, so you do it, let's say, at 2 atmosphere. So you increase the pressure inside. So now if you are at that depth, your lungs will be in equilibrium, right? So this is you here, that's the lung. So you're going to have 2 atmosphere inside because you are breathing that tank, the air from the tank, and you're going to have 2 atmosphere outside from the ocean. And you can change the pressure as you go down, you can increase the pressure. Okay, but there is a price to pay, because lungs and tissue, air can go into your tissue and the air from the tissue can go back into your lungs. So what's going to happen as you increase the pressure that you are breathing from the tank, because you are diving, you're going to have more pressure inside your lungs. So the nitrogen and the air is going to go to your tissue. That's totally normal. So what's going to happen if you go up, back up too quickly, the nitrogen here doesn't have time to go back to your lungs, and it's going to make bubbles. It's going to make bubbles in your blood, and you're going to have something called the bands. You can die, you can rip off your lungs, and accidents have happened. So if you are doing diving, scuba diving really deep, you have to learn how to go very slowly and to breathe out, taking all your nitrogen out. And if you don't do that, you have something called the bands, okay? And I'm going to show you a short movie, and then that will be it. And next time we're going to talk about atmospheric pressure, and then next time we talk about buoyancy, and then we'll talk about Bernoulli. So maybe 3 or 4 more videos. Okay, so this is a very cool video.
Gases have no fixed shape or volume. If they are not contained by something, gases will expand without limit. But if they are put in a container, the gas molecules will spread out to completely fill the space they're in. When Sean puts an air tank on his back, it is full of the air he needs to stay alive underwater. An air tank is one of the most important pieces of diving equipment. A typical tank holds about 2¼ cubic meters of air. Under normal pressure, that's about the same amount of air that would fit in a telephone booth. But in order to fit that much air into such a small tank, the air must be reduced in volume, or compressed. As more and more air is forced into the tank, the molecules of air are forced closer and closer together. As a result, the pressure in the tank increases. When all that air is jammed into the small dive tank, the pressure on the air inside the tank is more than 200 times greater than normal air pressure. Despite this increased pressure, the air inside most types of dive tanks still has the same mixture of gases as the air you're breathing right now, about 21% oxygen and 78% nitrogen. As you go deeper in water, the pressure pushing on your body by the water increases. Normal air pressure at sea level is about 100 kilopascals. At a depth of 10 meters, water pressure is 200 kilopascals, or twice the pressure of air at sea level. By the time a deep-sea diver reaches 100 meters, the water pressure on the diver's body is 10 times normal air pressure. Since the air inside the diver's tank is also under pressure, the air can still come out of the tank so the diver can breathe. But breathing pressurized air brings with it the potential for serious trouble. When gases are under pressure, more gas molecules will dissolve in a liquid, such as the blood and other fluids in a diver's body. For a diver, this means that more nitrogen will dissolve inside the body. The deeper they dive and the longer they stay underwater, the more nitrogen will enter their bodies. Normally, this isn't a problem because divers are trained to ascend gradually and make several stops on the way to the surface. This slows down the release of nitrogen from body tissues. It allows the excess nitrogen to stay in tiny bubbles, enter the bloodstream, and be exhaled from the lungs. However, if a diver rises too quickly, the nitrogen bubbles expand in volume as the pressure decreases. The process is similar to opening a bottle of soda.
Attends, c'est
Opening
enregistré.
the bottle slowly reduces the pressure gradually and prevents the formation of large bubbles. But when the bottle is opened quickly, similar to a diver coming to the surface too quickly, pressure is reduced quickly. Sean Gregg experienced this rapid release and expanded volume of nitrogen bubbles called decompression sickness.
Dizziness and nausea kicked in just immediately. And the only thing I could say to my partner was, get the gear off and get me in this boat because there's something wrong. And at which point I made it to the ladder of the boat, and that is the last thing I remember.
The expanding nitrogen bubbles can block circulation or press on nerves, causing the diver to bend forward in the intense pain that often gives this illness its nickname, the bends. But expanding bubbles in the bloodstream can even be deadly. In Sean's case, they blocked the flow of blood to his brain.
Sean!
Unconscious and perhaps seriously injured, Sean was rushed to the hospital. Along the way, Sean regained consciousness, but the nitrogen in his bloodstream was taking a toll on his body. The expanding nitrogen bubbles in his tissues and bloodstream were causing paralysis.
Here you are, you've diving all your life and no big problems, and all of a sudden one day you do everything right, but you're now going to be in a wheelchair.
Sean faced never being able to walk again unless doctors could find a way to get the nitrogen bubbles safely out of his body. His only hope lay in New Zealand, an island country about 3,000 kilometers away. John Duncan is a dive medicine doctor at a hospital in Auckland, New Zealand. He uses a hyperbaric chamber, an enclosure that can simulate the higher than normal pressure found underwater, to teach trainee divers about the effects of nitrogen on the body. But the main purpose of the chamber is to help people like Sean who are suffering from decompression sickness. After Sean was placed in the chamber, the air pressure was gradually raised to a level that simulated when Sean was deep underwater. The increased pressure inside of the chamber caused the nitrogen gas bubbles to reduce in volume and dissolve back into his bloodstream and body tissues. Then the pressure in the hyperbaric chamber was slowly decreased, allowing the nitrogen gas to be released more slowly and be normally exhaled through the lungs. Finally, Sean began to move. Over the course of several treatments, the nitrogen gas bubbles in Sean's body were compressed and decompressed several times. Miraculously, the spinal damage he had suffered began to heal. Sean still has some spinal damage, but with each passing day, he regains more and more of his mobility. With more than 90% of his movement back, he's again able to do the things he loves most, and playing with his children is at the top of his list. Gases have no fixed shape or volume.
Okay, so I'm gonna see you next time. I kind of went fast, but I hope it's